if you want to see how physicists and quantitative people can contribute to the effort to defeat the coronavirus, please feel free to take a look at my Twitter feed, and there's a link there to papers and so on. All right, well, I think so statistical mechanics can be useful, it turns out. All right, let's get down to business then. So what I'm going to talk about, so last time we talked about paramagnetism, and I walked you through the classical theory of that, and what you can see on the left panel. So the left panel is always going to show the previous slide, the previous blackboard, and the right panel will be the one which I'm writing on now. So I figured out a way so that you can see, if you're not catching up, you can see the previous blackboard, as it were. So what we did last time was we introduced this notion of these dilute salts, and we talked about what their angular momentum states were, and then we made a simple model of a paramagnet as a bunch of dipoles interacting with an external magnetic field. And then what we did was we worked out how to do the statistical mechanics and compute the partition function, as shown at the top of the screen up here. And what we did was we found that because it's a non-interacting system, the partition function factorizes into a product of partition functions for one spin, and then we did the sum over states as an integral over the solid angles and computed its partition function. And then we computed the magnetization in the z direction by simply taking the expectation value of the magnetic moment in the z direction. And that gave us the formula that you see at the top of the screen, which we, of course, evaluated by our usual trick of differentiation. And in this case, the differentiation is a derivative of the free energy with respect to the external magnetic field H. And then what that gave us was a rather complicated function, which we analyzed. The complicated function is shown in the middle of the page, this thing with hyperbolic cotangents, which is known as the Langevin function. And then we worked out the asymptotics of that, and those asymptotics gave us Curie's law. So that was the end of the classical calculation. And so now what I want to do is I want to move on and do the quantum theory. So let me summarize for you some of the results that you may have seen from atomic physics. And I'm not going to go through them in detail. They're in most quantum mechanics textbooks. So the main point is that what quantum mechanics tells us is that if I want to know the magnetic moment, that is a function of the total angular momentum state, where J is L, the orbital angular momentum, plus the spin angular momentum. And the formula that you end up deriving is this one. So E over 2mc, this is in CBS units, and the G is a factor that comes from adding up angular momenta, and you can do that geometrically. And so this is known as the Landé factor. And it's given by this formula. So I'm just going to write it down, and I'm not going to go into how you prove it. So that's how you compute that, and then what we're going to be interested in is the z component. And so the Z component is, as you know, just given by the magnetic quantum number. So mu Z is just equal to G, this lambda G factor, times E over 2mc, and then the H bar times m, where m is the quantum number, and m runs from minus j to minus j plus 1, blah blah blah, all the way up to plus j. So that's the range of the magnetic quantum number in the Z direction. And then what that means then is that we define this to be G times a quantity called mu b times the number m, and mu b is known as the Born magneton. A wonderful name, and this has the value E h bar over 2mc. So that's the setup. So now what we have to do is we have to compute the partition function, and just as we had in classical stat mech, what's going to happen is that the partition function is going to factorize into a product of the partition functions for one spin. So all we have to do then is compute this, and the partition function for one spin is now the sum over the states, and the sum of the states we can do by summing over the magnetic quantum numbers, and they go from minus j to plus j, and then our Hamiltonian is e to the minus mu beta h, so that looks like e to the beta times g, or magneton, the magnetic quantum number m, times the external field h. And so that's our expression for the partition function in the canonical distribution. And I'm going to write that in the following way. I'm going to write this as the sum from n is minus j to plus j of e to the x, e to the x times m over j. And I want to make it like normalize m by j because that's the limit of it. And then this quantity x is a dimensionless measure. Of the field energy compared to thermal fluctuations. And what is it? So this x is then E h bar. Nope, it's not. It's let me take that out. So x is G mu b times JH over KBT. So this is, in some sense, the analog of what we had before for the classical case. So in the classical case, we had a variable x, which was beta. I want it to be yellow. Why isn't it yellow? Oh, that's weird. Why does that not work? Well, I don't understand why the colors aren't showing up. 1 second here while I figure that out. Well, it works there, but why doesn't it work here? Huh, don't understand that. Okay, well, anyway. Okay, so back to the script. So this is just a geometrical series, and so since it's a geometrical series, you can just compute it. So Z1 turns out to be this. So it's e to the 2j plus 1 x over 2j minus e to the minus 2j plus 1 x over 2j divided by e to the x over 2j minus e to the minus x over 2j. And that's something that you can check just by summing up geometric oscillators. Okay, so if I then go ahead and compute work out this series, so what I get is that Z1 is equal to the hyperbolic sine of 1 plus 1 over 2j times this dimensionless field strength over the hyperbolic sine of x over 2j. So that's the result of writing that in this way. And then what I can do is I can compute the magnetic moment in the z direction just by the same formula that we had classically in d by dh of the logarithm of z1. In other words, the magnetization is just the derivative of the Helmholtz free energy with respect to the external magnetic field. And so now you have to just differentiate that function. So it's kind of a mess. But what you end up with is that mz is equal to n times g times b times j into this thing. So let me write it out. It's 1 plus 1 over 2j cof 1 plus 1 over 2j times x minus 1 over 2j cof of x over 2j. So all I've done there is nothing more complicated than doing the derivative. And this quantity that we have in the curly brackets, so this quantity.
Esther, could you bring back the other page really quick?
Which page do you want to have?
That one. Yes. No, scroll to the right.
So it's going to the right is the page I'm already on, isn't it? Oh no,
That one.
this one. Sorry, I didn't flip it. Yeah.
No problem.
Okay, yeah, if I forget to do that, just don't hesitate to remind me. So this thing here in the curly brackets, I'm going to call bj of x, and that is called the Brillouin function. So that's the exact formula. Any questions about this before I go on? And yes, Viva, thank you. I have started to record. Any questions about the formula, and I'll show you what the asymptotics look like. Okay, so let's do that. So now what I'm going to do is so let's just say that's the next thing we want to do is the asymptotics of this function. So that's the first thing. And then the other thing that we want to do is I want to look at the classical limit. So I want to ask, if I take this quantum calculation and now take the classical limit, will I end up reproducing what we did before on the classical behavior? So let's get into that. So first of all, let's sketch what the function looks like. So if let me just look at the small asymptotics. So for small x, what do we get? So then I can simply do a power series expansion. So what I get is that bj of x is equal to 1/3 into 1 plus 1 over 2j times x plus higher orders in x. And so that tells us that near the origin it's going to be linear, and so we're going to get the Curie's law. So that means that if I take this limit, then mz is going to be then. So I'm just going to take the linear term. So mz is going to be n times g squared times mu b squared times j plus 1 over 3 kBt times the external magnetic field. And this quantity here is basically, this quantity here is essentially the susceptibility. And this formula mz is again some constant. Let's call it the Curie constant, divided by T times the external magnetic field, and then there's corrections that will go as higher powers of the magnetic field. So what that means is that this behavior here is a linear behavior. Oh, I'm going to take that out. Not a good color, too dark. So this is the linear response regime, and the Curie's constant. So what we see then is that we do indeed get Curie's law, which is that the magnetization is proportional to H. So that's Curie's law, and what we end up with is a prediction that the Curie constant is equal to mg squared or magneton squared times the angular momentum over 3 times kb. So let's just try to plot that. So I'm going to draw the axes like so. So this is going to be x. This is going to be the one function. And asymptotically, for large x goes to the value 1. For 0, it goes linearly, and the slope, as you can see from the formula, the slope for the linear term depends upon j, and the bigger j is, the smaller is the slope. So it's going to go like this. So this would be j is 1/2. And then if I want to do, for example, j is equal to 1, and that would be something like that. And if I did something like j is equal to infinity, or j tending towards infinity, it would look something like this. So so that's the behavior. Now, why is this useful? Well, we already know what the values of j are because we worked them out last time for the different dynamic magnetic salts, and so we can actually compare the data for these particular salts with these predictions. So so back earlier on, last time over here. So here, for example, we have the different j values, and those different j values, you can see at the top of the screen there, those different j values can then be plugged into this formula and the susceptibility measured. So what do we get when we do that? So I'm not going to plot the data. Oops, wait, how do I get rid of that? Thing. So the data when you plot it basically falls right on these curves. Okay, so now we can make a nice prediction. So now let's look at the classical limit. So how would you think that the classical limit is obtained? So we've seen before that when you get to classical limits, what you want to have happen is that the energy level spacing is small compared with kBt. Or you can say, let's take kBt to be fixed, and then let's make the energy level spacing go to 0. Now, the energy level spacing in this case depends upon upon J. So what's going to happen is if I have space quantization, as they used to call it in the days of atomic physics. So basically, you have a state that is up, then a state that is like this, and then a state like that. So that would be J equals 1. And then if you had J is equal to some higher number, what you would get is that you would get something like this, and so on and so forth. And so what you want is that if you want a classical limit, is when the spacing goes to 0, i.e. J is going to infinity. So in other words, the spacing between these different quantization states is something that will depend on J. And so as I make J much larger than 1, and I get something like I've drawn over here, and so what I get is that that in the limit J goes to infinity, the spacing goes to 0, and there's no quantization of the directions. So when I take J going to infinity, what I'm going to do is define the classical magnetic moment as mu is equal to G times mu B times J, and note here that J itself is a function of J, and what I'm going to do is we take the limit that J goes to infinity, but G times J is equal to some finite number. And so that gives us the classical moment that I've drawn for you up here. So then what happens to the Brillouin function So what I have to do is look at Bj of x, and as I take the classical limit, the j goes to infinity means that terms like 1 plus 1 over 2j, those terms just go to unity. And so what that tells you then is that this complicated form that we've had over here, so this term and this term, and then this term and this term, you have to take those j go to infinity limits. And when you do that, you can convince yourself that Bj of x goes as cof x, and then I get 1 over 2j, that's this term over here, but then I also have the j go to infinity limit of cof x over 2j, and its behavior for large, for small values of j, in other words, large values of its argument, is linear, so that goes to 2j over x, like so, and then the j factors cancel out. And so what I end up with is that this thing ends up as being cof x minus 1 over x, and that's just the Langevin function of x. And so then what I've got then is that the magnetic moment in the z direction is equal to n times the classical magnetic moment times the function cos of x minus 1 over x. And that agrees completely with what we calculated before for the classical. Okay, so any questions about the classical and quantum paramagnetism? Cheng Hao, you have your hand raised.
Yeah.
Do you have a question?
Yeah, so I don't get why when J goes infinity, like with the spacing between the energy spacing is more over KBT is smaller because the energy difference seems to like the G mu B J, right? The mu times H, and I don't think that will change significantly when we pick the J. Let me check the energy difference.
So if you look in the picture over here, I'm just drawing. So if I have spin a half, then my spin can either point up or down like that. So the component in the z direction is +1 or -1. If I have spin 1, then what I get is it points up like this. Mz is 1 or 0, disappeared, or -1. So the spacing now in the z direction, which is what we're interested in, has now gone from +1 to -1, which is 2, to now +1 to 0, which is 1, and 0 to -1, which is 1. So the spacing is smaller. And if I have spin 2, then I can go 2, and then I go 1, then 0, then -1, then 2. And then if I look at the projections, so maybe it would help if I drew it like this. So let me draw the axes. Okay, so this is the z direction. So if I have for example then this would be s is a half. So this is +1 and -1. So s is 1/2. Then what I get is the spacing is +1 -1, which is 2 in these units. If I have if I have 1/2, 0, and -1/2, so that would be s is equal to 1. So then what I get? The spacing is +1 - 0, and 0 -1, so that is +1. So the spacing has got smaller. If I had s is equal to 2, so what I would have is this. And now if I look at the component in the z-axis, so I look at the component of the spin vector on the z-axis. So the projection is smaller as s gets larger and larger. And so so it's that spacing in the z direction that is the important thing. So it's the spacing. I need to clean my screen because of my hand. So it's the spacing in the z direction that that is the thing that has to be small with respect to kt. So t can be fixed, and j goes to infinity. So they're equivalent limits. So just as we can think of strong temperatures and weak fields, or we can think of it's a dimensionless quantity. So I can either make the numerator big or the denominator big, and that's how I change it. So that's why this is the classical limit. So does that answer your question?
Well, I think this figure is a little misleading because when the j goes infinity, I mean the magnitude of the z direction, the maximum magnitude should be the mz, right? The m should reach the j. The j, I mean the z component, which is we denoted by the m. The maximum m should be j, right? And the difference between them should always be 1. So the energy difference should be g mu b times h. And well, I just think they are constant. Maybe I just don't understand.
Yeah, I understand your question. You're saying that the length of the vector gets bigger, so the change in the actually I agree with you. The change in the projection is always going to be is going to be 1. That's what you're saying.
Yeah. Yes.
Yeah, that's true. I agree with you. That is true. But the point is that I guess the answer. I didn't really say it right. I agree with you. It's not just that the projection is getting smaller. It's that the number of states that you can. This is really what I'm trying to say. The number of states that you can access is going to infinity because it's not quantized classically. So it can point in any direction classically, but in quantum mechanics, it's restricted to the eigenstates are restricted to be in these discrete vectors. So when j goes to infinity, you have more directions in which you can point. And that's really the main thing.
Okay, thank you.
Yeah, I agree with you. I think what I wrote here is less to the point than that. Okay, so let's move on now to the next major topic, and the next major topic I want to go over is the harmonic oscillator. So let's talk about that. I just want to just get my hand off the screen. So that the words show up better. Okay, so this didn't happen last time. I had a smaller iPad last time. Okay, so now what we're going to talk about is the harmonic oscillator. Okay, so of course everything you can solve in physics is a harmonic oscillator. So it's very important to work out the stat mech of harmonic oscillators. So let's, what we're going to do first of all is we're going to do one harmonic oscillator, and then what we're going to do is an infinite number of harmonic oscillators, and that will lead us into black body radiation and some remarks about quantum electrodynamics. So let's start off then with one dimension and 1 degree of freedom. So we're going to and the most important thing, which I didn't say, is I'm going to start off with it being classical. Okay, so then our Hamiltonian is just 1/2 omega squared q squared plus p squared over 2n. So then we can work out the partition function. So Z1 is going to be, well, we know how to write down the quantum state in classically. So it's 1 over h, the integral dp dq, and then the Boltzmann factor e to the minus beta times the Hamiltonian. And that Hamiltonian is going to factorize because we have the part that is the kinetic energy over here, and then the part which is the kinetic energy over here. And so we can factorize those integrals, and so what we get when we do that is that Z1 is equal to 1 over Planck's constant times 2 pi over beta m omega squared, so 1/2 times 2 pi m over beta to 1/2 for the other one, and that then just gives us h bar omega over kBt inverse. So that's the partition function for one oscillator. Okay, so now let's do n non-interacting oscillators. So now I'm going to write the Hamiltonian is now the sum from I equals 1 to n. Now I have the same functional form for the Hamiltonian for one oscillator, but now it depends on its momentum and its coordinate h. It depends on the qi and the pi for that particular oscillator. So this thing here is the oscillator number. And now we can just plug into the formula. So that then tells you that Z n is equal to Z1 to the power n, and that means it's just h bar omega beta to the power minus n. So again, completely trivial. And then I can write down from this what the Helmholtz free energy is. So if I write down the free energy for n oscillators, that's just equal to n kBt times the logarithm of h bar omega over kBt. And then once I know the once I know that, then I can compute the entropy. And then the internal energy is from the free energy is just df by dt, df by dt. So that turns out to be n times kBt, and then the heat capacity and the is just n times is just n times kb. So that's the statistical mechanics then for a classical set of classical harmonic oscillators. Okay, so now let's do it quantum mechanically. Wherever there's a smudge, it makes it difficult to write. So what we're going to do for the quantum case is that we know that the energy levels are just given by n plus 1/2 each bar omega, where omega is the frequency of the oscillator. So when I want to compute the partition function for one harmonic oscillator, all I have to do is sum over the quantum numbers, n going from 0 to infinity, of e to the minus beta times the energy, and the energy is just n plus 1/2 times each bar omega. And again, this is just a series, because there's n and there is n, so we can simply work out that formula, and so what you get is that this is equal to e to the minus beta h bar omega over 2. That comes from the 0-point energy, and then the summing up of the rest of the series just gives you 1 over 1 minus the term that is being summed, which is this one. Okay, so that's the partition function for one oscillator. So now what happens when we have n of them? Well, it's just z1 to the nth power. Okay, so now what I can do is I can write down the corresponding formulae for the free energy. So let's write those down. So what I get, and these formulae are important ones, so I'm going to want to write them carefully. So this one is n is 1/2 h bar omega plus kBt times the log of 1 minus e to the minus beta h bar omega. The entropy is n times kb times e to the beta h bar omega over e to the beta h bar omega minus 1 minus the log of 1 minus e to the minus beta h bar omega. And the I'm going to go to the next page. And then the energy is n times 1/2 h bar omega plus h bar omega over e to the beta h bar omega minus 1. So that's the energy, and then finally the heat capacity. Well, that's not so important, so I don't think I'll write that down. Okay, so this answers the question. If I know the frequency of a harmonic oscillator, what its thermodynamics is. Okay, any questions about that before I go on to the next topic? Okay, so now what we're going to talk about is a very famous problem, and it's one that was, of course, the foundational problem in quantum mechanics. In fact, trying to understand blackbody radiation was how quantum mechanics was discovered. And let me also put in a plug for applied physics here. So you might think that, well, we make progress in understanding the fundamental laws of physics by doing fundamental problems. But this isn't quite true. Some of the work that was instrumental in discovering the black body radiation formulae that Planck eventually derived, some of that work was work that was funded by companies in Germany that wanted to make better light bulbs. And so they wanted to understand, if I heat something up, what color does it glow? And so these are very practical questions, but they ended up being important for making a profound new discovery. Okay, so what is our goal in this section? Is that we're going to consider electromagnetic waves in a cavity, and we're going to say that the cavity is at temperature T. And then, you know, then the question is, you can think of this cavity as being like an oven. And so the question is, what is the color that the oven has? And we can answer that by statistical mechanics. Now, the theory is really two parts, and it's very easy to get them confused. So the first thing we're going to do is, as always in statistical mechanics, is we have to solve a mechanics problem. And the mechanics problem that we're going to solve is the mechanics of electromagnetic fields. So what we're going to do is step one is solve Maxwell's equations. And from Maxwell's equations, what we're going to get is the energy of each normal mode of the electromagnetic wave. So that's the step one, and then step two is slightly different. In step two, what we're going to compute is the average energy of those modes. And we'll do that, of course, using statistical mechanics. So why is this a useful thing to do? Well, that means then we can in step three is that we can then calculate the energy in a wave number range or frequency range. And if we know the energy in a particular frequency range, then we can say what the color is going to be. So that helps us answer the question. Okay, so let's go ahead and do that. So let's start off with step one. So in step one, what we're going to do is we're going to solve Maxwell's equations. And we're going to solve them with zero boundary conditions. And that means that we're solving, i.e., the standing waves. Okay, so we know what the formula is going to be. If I look at the electromagnetic field as a function of space and time, what it's going to look like is something like this. So first of all, it's going to be a wave. So that's going to be an exponential factor. We're solving a wave equation. So the wave is going to go like the exponential of I times pi over L, a mode number n dot x, that's like k, then the frequency omega as a function of n times t. So that's that, and then the mode is going to be multiplied by its amplitude. So there's going to be an amplitude that will depend upon the vector n, and then lastly we're going to sum over all the modes. So we're going to sum from n x and y and z is from 1 to infinity, and n is just that. So that's the sum of a bunch of modes. And now, then how is the frequency depending on n? Well, we know that just comes from solving the wave equation. So the wave equation says that omega n squared is equal to c squared pi squared over L squared times nx squared plus ny squared plus nz squared. And this then is what we're going to define to be c squared times the wave number squared, e squared. So the wave vector k is just pi over L times n. Now, the thing I want you to understand is that these n's here, these n's are not quantum numbers. These n's are mode numbers. So this is these are mode numbers. And this n is a mode number. And this is a wave number. Okay, so that's this. Now the A's is an amplitude. So A is an amplitude, and it's given by this coefficient. So you might think that this A is a vector, and it is. So it should be a vector like this, and so it's an amplitude, and it should have 3 components. But there's another Maxwell equation that we've forgotten. We have in free space, what we know is that there's no sources, so div of the electromagnetic field is equal to 0. Otherwise, it would be given by something like Poisson's equation. So in free space, if div E is equal to 0, and so what that says is that actually because of div E is equal to 0, this is a constraint on the A's, and what that means then is because div E is equal to 0, that means that A actually has only 2 components. And so those correspond to the 2 polarizations of the wave. Okay, so that's step 1. So this was all purely This is all purely classical. So then what happens then when we put in quantum mechanics? So when we put in quantum mechanics, then actually it's actually quite easy, because from the point of view of writing down the electromagnetic field, what we have is a bunch of modes that are superimposed because of Maxwell's equations are linear. So what that means is that we can simply add up the energy of all of the modes and then take the thermal expectation value of those things. So basically, the basic idea is that each mode is a harmonic oscillator. With frequency omega, which is omega of n. So you tell me what mode it is, I can tell you what frequency it is, and then I just say, well, that is an oscillator with that particular frequency. And so then I can compute the energy of that mode. And we know that the average energy is going to be 1/2 h bar omega, but now omega depends on what the mode itself is, plus the thermal part, h bar omega over n over e to the beta h bar omega over n minus 1. So where does that part come from? So this part is the 0-point energy. And that 0-point energy part that you see on the other blackboard, that part is just what is happening over here. Well, I know why it doesn't work. You can do it like this, right? There we go. Okay, so that's the 0-point energy, and then this is the thermal part. And so those two things correspond to each other in here. So the only difference is that we're just replacing the omega by omega of n. Okay, so now that we have that, then what I need to do is I now need to compute the total energy. So what is that? So that's just the sum over the modes of the thermal expectation value of E of n. And all the quantum mechanics has come into this thermal average. So that's where the quantum mechanics came from. Okay, so now what we have to do is we're going to evaluate this integral, this sum, and the way, of course, we're going to evaluate it is we're going to turn this sum over modes into an integral over modes. Just as we have done before. So let's go and do that. So let's just write down the formula and then discuss what it means. So then what we get is that U is equal to one other thing I forgot to mention is there's a factor of 2 in here, and that factor of 2 is due to the polarizations. because for each mode, I have the amplitude, and there's two independent components, so therefore there's a factor of 2 when I add up the energy for each mode. Okay, so then what I'm going to get is I'm going to get 2 times the sum over k, and the k has to be, these ends go from 1 to infinity. And so this sum is k in the first octant. Of h bar of k over e to the beta h bar omega of k minus 1. And then I have it's the sum over the k's of h bar omega of k divided by 2. So this comes from the 0-point energy. And this is the excited parts. Okay, so the problem is this. So there's a problem. And the problem is that the second term is the sum over k of h bar omega of k over 2, and omega of k is equal to the speed of light times the absolute value of k. And where does that come from? Well, that comes from this formula over here. Okay, so because of that, what that means is that when we sum over k, the sum over k of k is a number that is basically infinity. So this thing over here is equal to infinity. So that's a big problem. So the way you can solve that problem is by a renormalization. Okay, so renormalization probably sounds something very complicated to you, and you've probably heard about it. Some of you are taking field theory, so you know about the work of Feynman, Tomalaga, and Schwinger that won them the Nobel Prize in Physics for doing the quantum theory of electrodynamics. And the two should get cancelled in the term. That is correct. It gets cancelled, but it doesn't matter. Because we still have this infinity. So what the renormalization procedure is something very complicated. It's basically the following. What I do is I take this infinity over here, and I say that this infinity is actually equal to 0. Okay, and that's renormalization. So what we're saying in effect is that the vacuum has some certain energy, and then what we're doing is we're just looking at the energy with respect to the energy of the vacuum, and so we can ignore what is the energy of the vacuum itself, even though it is formally infinite in this way. So that may sound like a bit of a fudge, and it's even worse than that, because you might say, well, wait a minute, suppose I look at Einstein's equations, for gravity. Einstein's equations coupled to any energy as their source, and so this 0-point energy of the electromagnetic field would then be a strong source in the equations of gravity, and we're just simply throwing that away. So you may say, well, okay, that's the way it is. But this energy of the vacuum turns out to be a really physically important quantity because it affects the expansion of the universe. So if you look at modern theories of cosmology, some of you will know that there's a phase of the universe, a very early phase, where the space-time expanded faster than the speed of light, and is expanded due to the pressure caused by the vacuum energy density of whatever quantum fields were around at the time. So this term that we're sort of now throwing away and setting equal to 0 actually has a value, and that value actually has an observable consequence, at least when one starts to talk about general relativity and space-time. So then the next question is, well, is the universe really expanding as you would expect by having that vacuum energy density there? And the answer is no, it isn't. Most people until maybe 20 years ago thought that this effect was 0, that it was literally set equal to 0. And so then the question was, why is the universe fine-tuned? So there's no effect of the vacuum energy. Then people discovered that the universe is actually accelerating in its expansion, and so this thing then became known as dark energy. So in a sense, what dark energy is that this seems to not be 0 after all. And the people who discovered the dark energy and the expansion of the universe due to these effects, they also won the Nobel Prize. Now, this is still quite controversial. The evidence that they had for seeing dark energy came from looking at the expansion of galaxies and calibrating those correctly. And I've seen recent claims that those calibrations were in fact not done correctly. And so if that's the case, then maybe this whole picture of inflation of the universe and dark energy might turn out to not be correct after all. Okay, so what we're going to do is, for now, at least for this course, we're just going to ignore the 0 point energy, and so we're just going to work with the term over here on the left blackboard, which corresponds to the excitation. So let's write that down then. So we're going to ignore the 0 point energy. And so that says that the total energy is the factor of 2 for the polarizations, and then the density of states in k space, then times the integral from 0 to infinity of T3k, which is 4 pi k squared dk, times the frequency, which is omega c times k, divided by e to the h bar c k over Boltzmann's constant minus 1. And that's the final formula. So now what we're going to do is we're going to make a change of variables. So we're just going to define x to be h bar c k over Boltzmann's constant. And then when we do that, then what we get is that u is equal to, okay, and now this is a class question. So look at the formula on the left-hand side, at the bottom for the energy, and work out for yourself how many powers of temperature are there going to be there. So we're making the change of variable x is h bar ct over kt. So u is going to then be proportional to some number, which is just an integral, times some bunch of constants, times something related to kbt raised to some power. So what should that power be? Yeah, anybody want to give the answer?
Is it 4?
It should be 4. Thank you, Mark. That's right. It's 4 because we have this one factor of k over here, we have a dk over here, and we have 2 factors of k over here. So when we make a change of variable, this is going to go like kbt to the power 4th, and then it's going to be multiplied by a bunch of constants. So they turn out to be v over pi cubed times pi h bar c, and then we have the integral that we have to do. That integral is just a number which happens to be the integral from 0 to infinity of x cubed dx over e to the x minus 1. And again, you can work out what that number is. And so when you put it all together, what you get is that this thing is equal to v times pi squared over 15 h bar times c cubed times kbt to the power 4. And this kbt to the power 4 is something that you learned on your mother's knee. This, the fact that u goes like kbt to the 4th is the Stefan-Boltzmann rule. So that was known before it could be calculated. Now, the Planck formula. Oh, somebody raised their hand or made a question. So the integral is over the first octant, so it should be divided by 8. Yes. So some of those factors have been were taken into account. So anyway, so you can check these numbers to make sure that that I did it correctly. Okay, so let's write down now what is the energy in the frequency integral from omega to omega plus d omega. And so the way I'm going to answer that is I'm going to make a change of variables. Because omega is equal to ck. So then what I get is that u is equal to the integral from 0 to infinity d omega over c v over pi squared h bar c omega cubed over c cubed, and then 1 over e to the h bar omega over kbt minus 1. And I'm going to write that as obviously the energy is going to depend on how big the system is, so it's going to be proportional to the volume, and then there's going to be something that is an integral over all frequencies of some quantity, which I'll call u omega, the spectral energy density. And then we can read that the formula for that off from the integral above, and so what we get then is that u omega is just h bar over pi squared c cubed times omega cubed over e to the h bar omega over kbt minus 1. And this is a fantastic formula, and it's obeyed by black bodies, and the most spectacular observation of it has been looking at the microwave background of the universe. So back in the 60s, engineers at Bell Labs just could hear this sort of weird hissing in their antennas that they were measuring. This is Penzias and Wilson, and they eventually realized that this noise came from the microwave radiation that was coming to them from space. And then in the 1990s, the Kobe satellite was sent up there and into space and measured the microwave background with what was then the best precision, and it fitted the black body radiation formula precisely, and that's how we know the temperature of the universe is now about 3 Kelvin. So that the temperature of the microwave background is defined because it fits this black body radiation formula. And so this is of course was a great triumph. Let me make a couple of comments on how we're doing by time. We're nearly finished, so let me just finish the comments. So in the homework, you get to derive these results from a particle picture. So you all know about wave-particle duality. Here we've been talking about electromagnetic waves as electromagnetic waves, but you can also derive these formulae from thinking about photons. And so that's what I call the particle picture. And so you can derive this from the grand canonical distribution. And so that's something that you'll be able to do in the homework. This method works not just for EM radiation, but other waves as well, such as sound waves, and even the capillary waves. On the surface of helium. And so that will be another problem in the homework. So and again, when you apply this to sound waves, so the sound waves, those are called the phonons, as you know, and that gives you Debye's theory of heat capacity. So this black body radiation formula has many applications. Okay, so I think that's where I'm going to end today's lecture. So next time we're going to talk about the equipartition theorem, and also going to talk about another theorem, which is the virial theorem. Okay, so any questions about today's lecture? Okay, so whoever put their hands up, so just raise your hand and just go ahead and ask. Unmute your microphone.
Professor, could you just go over the renormalization part? I'm not sure I understood how setting it to 0 just solves it is okay, or how we
It's
can just
not.
proceed.
It's not okay. So there's two things in renormalization. One is worrying about the background energy. The things that Tominaga, Schwinger, and Feynman got the Nobel Prize for was not that. What they looked like was something different, which is if you're looking at, say, an electron in a magnetic field, electromagnetic field, looking at how its charge and mass get renormalized by polarizing the vacuum. So there's two things. One is throwing away the background energy, which is what we did here in a very cavalier way, and it's completely unjustified. And then the other is the more is asking a different question, which is trying to understand the how things that you observe in quantum mechanics change as a function of scale, and that leads into renormalization group. So my comments about renormalization were really intended just to say we don't have a good understanding of how to really remove the vacuum energy in an infinite system. So you can think of it in a way of just saying, well, there is, if the system size is finite, I have some energy, it's formally infinite, I will just simply, we will not ask where it goes, and we'll just look at what is the difference between the actual energy and that formally infinite background energy. So there isn't really, I can't really give you a good answer in terms of how to justify that particular renormalization step. So you shouldn't understand it, because it's one of them. I think it's still a mystery, which is how do you understand dark energy and so on and so forth. So these vacuum energies have either they have a real value, in which case you have to ask why they seem to be zero now, or why they're nearly zero. And if they have a real value, you have to ask why is it finite and not infinite. So there isn't a good answer to that. Okay. Who asked the question? I've forgotten. It was Abhishek.
I want to ask, do we have office hour today? Do you have?
Do I have an office hour today? So we can do it this way. So we can either just stay on this Zoom call. So this Zoom number will be the same all week, or all the rest of the semester. So we can either do that, or we can do Zoom on the same number at 4 o'clock. How many people would like to have an office hour? So I'm happy to do the office hour. We can either just stay on this call and just keep going. I do have many other things that I urgently need to do, but you guys come first, and so anyway, yes, we will have an office hour. Would it be from 3:30 to 4:30 then? Well, up to you guys. Actually, I'd like to take a quick break. So why don't we take a quick break and then resume at 4 o'clock? Now, if this number, so this number could work. So just use the same number for the class and join me at 4 o'clock. Does that work for everybody? Okay, great. Okay, so then I'll see you then in about half an hour. So and then we can try to do office hour through Zoom. Any other questions about the lecture? Okay, see you at office hour in a bit.